In the last few videos, we've been studying the problem of a mass attached to the end of a spring and then released so that it oscillates back and forth around the equilibrium position of the spring. In the last video, we learned how to write down a function which gives the position of the mass as a function of time. The idea is that we attach the mass to the spring and then pull on the mass so that the spring extends, so that the mass is then located at a coordinate x equals a. Then at time t equals 0, we release the mass so that the mass oscillates back and forth between x equals plus a and x equals minus a. Under these assumptions, the position of the mass as a function of time is given by x of t equals a cosine omega t, where a is the amplitude of the motion, omega is what we call the angular frequency of the motion, and omega is given by the square root of the spring constant divided by the mass. Other things that we have already seen in this module are the period of the motion. The period of the motion is given by 2 pi divided by the angular frequency. It is equal to 2 pi times the square root of the mass divided by the spring constant. We have also seen that the maximum speed of the mass occurs as the mass passes through the equilibrium position. That maximum speed is given by the amplitude multiplied by the angular frequency, or equivalently by the amplitude multiplied by the square root of the spring constant divided by the mass. In this video, we're going to do an example problem which uses all of these ideas. So what's happening in this example problem is that we have a 400-gram mass. We attach that mass to a spring with an unknown spring constant, and then we pull on the mass in order to extend the spring by 30 centimeters. The origin of our x-axis is located at the resting position of the spring, which means that the mass starts out at a coordinate x equals 30 centimeters. At time t equals 0, we're going to release the mass, at which point the mass is going to begin oscillating between plus 30 centimeters, minus 30 centimeters, plus 30 centimeters, minus 30 centimeters, and so forth. We are given that the maximum speed of the mass is 2.50 meters per second. So we would like to find the spring constant, the angular frequency, and we want to plot the position as a function of time for 2 complete cycles of the motion. Let's do part A, where we find the spring constant. Now, if you scan through the equations over here, you're going to find one equation where everything is known except for the spring constant. So why don't you see if you can find that equation and then solve for the spring constant. And once you've given that a shot, rejoin the video. So we're going to find the spring constant using this last equation for the maximum speed of the mass. So we have maximum speed equals amplitude times square root of spring constant over mass. So to get to the spring constant, let's square both sides. That gives us V max squared equals a squared times k over m. So just solve for the spring constant here. We get spring constant equals mv max squared over a squared. Substituting, I'm going to go to MKS units. So the mass would be 0.4 kilograms. The maximum speed was given 2.50 meters per second. We square that. And the amplitude is 30 centimeters, which converting to meters is 0.30 meters. We square that. Putting all of this into my calculator, I get for the numerical value 27.8. Now let's check and make sure that we have the proper unit for spring constant. I'm going to take all of the units here and copy down to here. So I have then kilograms times meters squared over seconds squared in the numerator, and then meters squared in the denominator. So what I will do here is cancel one factor of meters in the numerator with one factor of meters in the denominator. Notice now that the numerator is kilograms, meters per second squared, which is a Newton. The denominator is just meters. So this would be the proper unit for spring constant, newtons per meter. So we have that the spring constant is 27.8 newtons per meter. I'm going to go back in and put that into the figure. The next part of the problem is to find the angular frequency. So why don't you scan through what I've written here, see if you can find an equation that will help you find the angular frequency, and once you've given that a shot, rejoin the video. At this point, there are actually two different ways you can get the angular frequency. You could come over to here where it says Vmax equals A omega. And since we know both the maximum speed and A, you can then solve for omega. Or you can come up to here where we have the usual formula for angular frequency, omega equals square root of K over M. And since we now have both the spring constant and the mass, you can substitute into here to get the angular frequency. So I'm going to use this formula here, omega equals square root of K over M. So now substituting, K is 27.8 newtons per meter. M is 400 grams, or I can write that as 0.400 kilograms, and then square root. When I put this in my calculator, I get 8.34. But we want to make sure that we have the right unit, so let's do the unit check. Newtons per meter is the same as kilograms per second squared. Then we have down here kilograms. So kilograms cancels kilograms. Then we have 1 over second squared inside the square root. So when we take the square root of this, we get 1 over seconds, which I can also write as seconds to the minus 1, which would be the correct unit for angular frequency. So the angular frequency is 8.34 inverse seconds. Now we're going to do the last part of the problem where we plot the position as a function of time for 2 complete cycles. Position as a function of time is given by a cosine function, so we can start out just plotting 2 complete cycles of the cosine function like we normally would. To start, I'm just going to make a coordinate system. So I have time on the horizontal axis and position on the vertical axis. Now, unlike the previous video where I did this abstractly, in this problem, we have actual values of time and position that we want to represent in our graph. So we have to include units in the axis labels. So we're going to be plotting position in meters as a function of time in seconds. Now to plot the cosine function, I'm going to put in my bounding lines. Now the mass in this problem oscillates back and forth between 30 centimeters and minus 30 centimeters. Since I'm doing this in meters, I'm going to put in the maximum position as 0.30. The unit is given here by the axis label. Then the most negative position would be minus 0.30. Again, the unit meters given by the axis label. Now I'm just going to plot 2 cycles of a cosine function as usual. And I like to do this by making marks on the page as to where the plot is at each quarter cycle. Now to finish the plot, we want to put in on the time axis the time when the first cycle was completed and also the time when the second cycle was completed. So what was the time when the first cycle was completed? Well, let's come back to here. Over here, we have that the period of motion is 2 pi over the angular frequency. So I'm going to copy this over to here. Period equals 2 pi over the angular frequency. Now, we have already found that the angular frequency is 8.34 seconds to the minus 1. So 2 pi divided by 8.34 would be 0.75. Now we have seconds to the -1 in the denominator, which becomes just seconds in the numerator. So coming now to our plot, the period here gives the time needed to complete one cycle of motion. So the first cycle of motion would be completed at time 0.75. Again, the unit is given in the axis label. And the second cycle would be completed at a time 2 times 0.75, which would just be 1.50, again with the unit given in the axis label. So now we have done the problem. We have analyzed the motion of that mass oscillating at the end of the spring. We worked up the spring constant, the angular frequency, and most important, we are now able to plot the position as a function of time for 2 complete cycles, and including on the axes numerical values giving the spatial extent of the oscillation and also the times at which the cycles of oscillation are completed.